the cool thing is that we can jump not only by constants, like the previous example, but also by entire functions, like the next example. So in particular, let's find the Laplace transform of g. There's a reason for this, where g starts at 0 and then suddenly becomes a cubic function. So if you want to draw this, it's 0 until at 2, we get t minus 2 cubed. And the cool thing is, it's the same process. So first, write g in terms of UC. Of UC, again, of our Heaviside functions. And what you do here, you start at 0. At 0. And then you jump at t equals 2 by the function t minus 2 cubed. So you will get a plus t minus 2 cubed u2 of t. And so what is g? Again, you start at 0, so 0 plus that jump, which just becomes t minus 2 cubed u2 of t. This is the function g. Now, it looks like magic that I just pulled the bunny out of my hat, but I do want to show you that it makes sense. So once again, g is 0 before 2 and t minus 2 cubed after 2. But it makes sense in terms of this definition. So note, makes sense. Because, well, if t is less than 2, we want g to be 0, but in that case, g of t, which is t minus 2 cubed, u2 of t, u2 in that case is 0. So we do get that g is 0. And if t is greater or equal to 2, then g is t minus 2 cubed, u2 of t. In that case, u2 is 1, and we get t minus 2 cubed. So in fact, it checks out. It's really t minus 2 cubed times this off and on switch. And now we want to take Laplace transforms. Just like the previous example, step 2. Take Laplace transforms. And what I'll show you now is first the slow way, which just uses the definitions and is very intuitive. And then I will show you the fast way. So once again, remember g was t minus 2 cubed, u2 of t. Again, I'm going very slowly here because I know it's a very difficult topic. So slow way. Okay. Let's calculate the Laplace transform of g. Well, by definition, it's the integral from 0 to infinity of g. So t minus 2 cubed, u2 of t times e of minus st dt. But remember, u2 has a piecewise definition. In particular, before 2, it's 0. After 2, it's 1. So once again, it makes sense to split up the integral from 0 to 2, t minus 2 cubed, in which case u2 is 0, and then e of minus st dt, and the integral from 2 to infinity of t minus 2 cubed of 1 e of minus st dt. Now the integral with 0 just becomes 0, so we're left with integral 2 to infinity t minus 2 cubed e of minus st dt. Now, this almost looks like a Laplace transform because we have e of minus st. The only problem is we start at 2 and we have this t minus 2, whereas we want the integral to start at 0. So it's natural now to use a u sub. So let's use u equals t minus 2. In which case, I mean, du becomes dt. It's not a problem. And we indeed start from 0 to infinity. So it becomes integral from 0 to infinity of u cubed e of minus s. And remember, so in this case, t is u plus 2. So t times u plus 2 du. And well, let's split up this exponential term. So integral from 0 into infinity, u cubed e of minus su, and then e of minus 2s du. But the nice thing is, this e of minus 2s, it doesn't depend on u, so you can pull it out. And what we get, it's the e of minus 2s integral from 0 to infinity u cubed e of minus su du. But notice this becomes a Laplace transform because it's the integral of the cube function times e of minus su. The fact that we're using u or t is very irrelevant here. So in fact, this becomes e of minus 2s and Laplace transform of t cubed. And yes, Laplace transform of t cubed because it's Laplace transform of the cubic function. If that confuses you, just use another u sub, u equals t, and then write the integral in terms of t. And last but not least, to actually get the answer, we get e of minus 2s. Remember, a Laplace transform of t to the n is n factorial over s to the n plus 1. So it's 3 factorial over s to the 4th. And so this becomes e of minus 2s and 6 over s to the 4th. That's our answer. So that was the slow way where we did it using the definitions. But now, what is the faster way? Well, if you calculate a Laplace transform of g of t, it became Laplace transform of t cubed, but with this extra exponential term. So faster way, and then I will write this in terms of a formula very soon. So L of g of t, that was Laplace transform of t minus 2 cubed, u2 of t. And notice, at some point, we got this extra exponential term to appear, e of minus 2s times Laplace transform of the cubic function. So e of minus 2s, and then 6 over s to the 4th. So what did we do? We took Laplace transform of shift and jump, and what happened, there was this exponential term that came out, and Laplace transform of the unshifted version. So if you want a general fact here, the Laplace transform of shift and jump, so in other words, Laplace transform of t minus c times uc of t, shift plus jump, is exponential term times Laplace transform of unshifted version. Unshifted. So let's do an example with this formula. And by the way, again, this will be given to you on the Laplace transform table. So let's find the Laplace transform of, let's say, cosine 2t minus 6 u3 of t. Notice by comparison, here we have a uc, here you have a u3. So c would be 3. But we just need to write cosine of 2t minus 6 in terms of t minus 3. So 2 times t minus 3, u3 of t. And in that case, what is our function? So it's cosine of 2 times shift. So f of t is cosine of 2t. So what this tells you that an extra exponential term comes out, e of minus 3s, and then Laplace of unshifted version, cosine of 2t. And so this becomes e of minus 3s, and I think cosine of 2t becomes s over s squared plus 4. So moral of the story is, whenever you use a shift and jump, an exponential term appears. And the next example will be more practice with that.